Welcome back. In the last video, we looked at neural networks in sklearn. In this video, we look at neural networks with the Keras package. Keras is available as a package in R, and it's also available as a package in Python. We'll look at the Python implementation in this video. Keras was developed by Francois Chalot at Google. Keras is basically an interface to facilitate deep learning. It can run on top of TensorFlow or other deep learning packages. We'll show it running on top of TensorFlow. This website, keras.io, has tons of tutorials as well as installation instructions. There are two separate books by Chalot and his collaborators. One is Deep Learning with Python and the other is Deep Learning with R, both available from Manning Publishers. I highly recommend these books because they not only give you the practical steps on how to do deep learning, but they give you a lot of conceptual background on why you're doing what you're doing. Keras works well on Mac or Unix, but it can have some issues in Windows. For this reason, I'm going to demonstrate Keras in Google Colab. Google Colab is a free service. It provides a Jupyter Notebook environment to run machine learning on a virtual machine in the cloud. To get started, go to this link, colab.research.google.com, and log into your Google account. The first time you'll need to specify a folder in your Google Drive where notebooks you create in Google Lab will be stored. When you log into Colab, you'll see a screen like this. This pop-up shows that your first option here is a welcome page that gives you an overview of the service. Once you've created notebooks, you'll see them down here. You can click on them to open them, or click on the Google Drive icon over here to see where they're stored. On the bottom right is a link to create a new notebook. Notice the bar at the top of the pop-up provides a lot of options, including a link to GitHub where you can upload a notebook or link directly to one in a GitHub. We're going to look at one of the sample programs in Keras, the MNIST program. I have a link to the original code here. You can see all of my imports. I'm importing different things from Keras, including the dataset MNIST, the models, the layers, and optimizers. We'll talk about what all of these mean. The MNIST dataset contains pre-processed images of handwritten digits. The images are in a 28 by 28 grid of pixels. The dataset's already divided into train and test. The target is one of the 10 classes, one class per digit 0 through 9, so this is a multi-class classification example. This block of code downloads it, which will take 2 or 3 minutes depending on your connection. And then we want to reshape the 28 by 28 dimensions into one long 784 dimension, make sure they're floating point, and then divide by 255. The reason we're doing that is that the images were stored in a grayscale from 0 to 255, so this will make them floating point. And then we printed out the shape here, and you can see that there are 60,000 in the train set, 10,000 in the test set. We'll use some built-in utilities to convert our labels into categorical data. And then we design the network. The most basic type of network is a sequential network. This is just a basic feed-forward neural network. And then we can add different layers. I'm adding 2 densely connected layers of 512 nodes each with ReLU activation. My input shape on the first one has to match my training data. After each of those layers, I have a dropout rate of 20%. So what that does is randomly take 20% of those parameters that were learned and delete them. And that's a little bit counterintuitive, but it turns out that this helps the model not learn noise. My final layer is my output layer, and it has to have 10 classes. And I'm using softmax activation What softmax does is take the probability space and divide it into the 10 classes appropriately so that the digit with the highest probability is the one we'll choose. All right, this didn't do anything but design our model, and printing out our summary here, you can see what we've done and the total number of parameters. Before we can train, we need to compile our model, and it needs 3 more parameters. It needs a loss function. Categorical cross entropy is good for multi-class classification. It needs an optimizer. This is a variation of backpropagation. And it needs a metric to know how well it's doing. So this is classification. We can use simple accuracy. The actual training comes in here in the fit method. And you can see where those parameters are used that we set up before. And for validation, we'll use our test sets. So this takes a couple of minutes to run. It took about 9 seconds per epoch, and we had 20 epochs. And at each step, it tells you the training loss and the validation loss and accuracy here. So in these 20 epochs, the training got it from about 96% up to 98%. All of the training information is stored in this history variable, so we can take a look at that. We can use items stored in the history variable to make some plots here, and I've imported matplotlib to do this. And I'm plotting in orange our accuracy for test and train. To see what exactly you could plot, you can ask for the keys of that history variable, which we can see is actually a dictionary. Finally, if we want to evaluate how well we did, we could see that we got about 98% accuracy. This is just a quick run through to show you the basics of how you use Keras in Google Colab. We'll drill down into more of the details. And notice it gives you a nice usage up here of RAM and disk. One other thing I want to point out is that up here in runtime, you can change runtime type. The default is to not have a GPU or TPU. Since this is a free service, it's best to keep it as none. If you really need this, you can use them, but at some point you may not have free access anymore. So I would keep it here until you have a situation where either you're ready to upgrade your account or it's just a one-time quick problem that you think won't get you over whatever the free limit is. The data types used in Keras and TensorFlow is the tensor, which is just a generalization of vectors and matrices to arbitrary numbers of dimensions. The dimensions are called axes. There's some nice documentation on the underlying mechanics of TensorFlow, which you can find at tensorflow.org. And let me go down here to an illustration that I like. So the rank is the number of axes. We also have a shape and a type, either integer, double, and so forth. For data similar to a data frame, we would have 2D tensors of shape, number of samples, number of features. If we have time series or sequential data, that would require 3D tensors of shape, samples, time steps, features. Images would require 4D tensors of shape, samples, height, width, and channels, or some such variation where channel could be 1 for grayscale or 3 for RGB data. Video will require 5D tensors with the 5th axis for frames and the other similar to images. In the chapter I have some guidelines for how to design your network. Much like the neural network in sklearn, there's going to be some trial and error, but here are a few guidelines you can consider when designing a network. I also have some advice on how to choose an activation function, optimization, and loss functions. Next, we'll look at an example where you can bring in your own data. Before we move on, let's look in the File menu. Notice that you could download your notebook either as a Python file or as a notebook. Save in various places, rename, upload, and so forth. But notice we could print here, and this would be good for homework or projects, and one of your options would be here to save as PDF. So I'm going to go open a notebook. I'm going to look at a regression task. This uses a data set from the UCI repository on air quality. It measures particulate matter, and so it's a measure of how polluted or clean the air is. So here are the steps you need to go through to upload a file from your own computer into Google Colab. So these two lines, when you run them, will let you choose the file and then upload it. And it surprisingly uploads pretty fast. If you get an error thrown here, make sure you're using Chrome, and also make sure you're not in incognito mode. Other browsers work, but Chrome is probably the safest. So we need some more code here to actually read it in. We need to import I/O, and then this code right here will load into a pandas data frame what you uploaded in the previous block. Then we're ready to go with any data exploration that we want. So we're looking at the data, and what we see here is there's a year, month, day, and hour. There's the particles that we want to be able to predict based on other features like dew point temperature, atmospheric pressure, and so forth. Let's do a train test split. We have about 30,000 rows in training, about 8,000 in test. Let's try linear regression and sklearn. And we get a root mean squared error of about 79 almost. All right, for neural networks, we always want to scale the data. Here I'm going to use sklearn scalar, fitting it to the training data, and then applying that scalar to both train and test. And now let's get into the Keras. Here I have 512 nodes in the first layer with dropout, 128 in the second with dropout, one node for my output layer. I'll compile. Here I'm going to use mean squared error for my loss function, still using backpropagation, and mean absolute error as my metric in training. My epochs is 100, so I'm going to hit pause on the video and come back. I had verbose set to 0, which didn't give me any feedback, and with 100 epochs, I really like to see that it's doing something. So I hit stop, the same place you can hit run, you can hit stop, and change the verbose back to 1. And we see that my mean absolute error started off at almost 46, and by the time we got through 100 training epochs, which took several minutes, it was down to 34.8. Again, we can plot and watch our errors go down, and evaluate and see that we got a root mean squared error of 52.6, which is quite a bit better than the linear regression that we got earlier of 79. And we got a mean absolute error of 34.8. So this definitely did better than linear regression, but the question is it really good? Here I've printed out for our target column some descriptive statistics, and we see that the range is from 0 up to 994, so almost 1,000 I guess. And the standard deviation is 92, so being off an average of 34 is actually pretty good. In this video, we ran through a classification example and a regression example using Keras. The Keras framework makes it easier to experiment with different architectures. And using Google Colab may be faster than your own system, depending on whether or not you have a GPU. In the chapter, I have a brief description of other models besides the sequential model that we used here. Convolutional neural networks are often used for image data. Recurrent neural networks and LSTMs are often used for time series or text data. You can check out many examples in the Keras.io website or in the 2 books I mentioned earlier. What we did in these examples is not that deep in terms of deep learning. We only had 2 hidden layers. The Keras framework would make it really easy to experiment with more layers to get a truly deep network, but that of course would increase our training time. And we saw that even with a not so deep neural network, we get good results. Why is deep learning so popular? There are 2 simple answers to that question. One is that we have more processing power on our own machines, not to mention in the cloud. And 2, we have more and bigger data.